So in the previous section, we talked about um, so so one way to measure the coverage. So we talk about how to measure the coverage based on the input space, right? And we mentioned there's another way is to cover to measure the coverage of the code or to measure the coverage of the implementation. Okay, so this is also the coverage that we already mentioned previously in our lecture. Okay, so code coverage. So how to cover code? We have two ways, right? First way is to ignore the structure, just to consider the code as a plain text. How many lines we cover, or how many statements we cover. Okay, just called statement coverage or line coverage. Okay. Second way is to consider structure. But two approaches: branch coverage, path coverage. We talked about statement or line coverage, branch coverage, and path coverage before. So here I just briefly reiterate. So what is line coverage, what is branch coverage, and what is path coverage? So basically, line coverage or statement coverage is we want to cover all the statements in the source code, right? So here, if we want to cover all the statements, so how many test cases we need? In this example, the first the part on the left is the pseudocode, and the figure on the right is the full graph, right? If we just have one test that traverses through 1A, 2C, right? A, after one we go to A, for example. After two, the decision will go to C, right? 2C, and 3D, and E, then 4G, 5H. In this way, we cover all the statements, right? We just need one test case to cover all the statements. What about if we want to cover all the branches? So here we didn't cover all the branches, right? For example, after the branch of 2, we didn't cover the branch B. Even there's no statement in B, but we didn't cover that branch, right? So the branch coverage, so how can we design a test case, right? So the first one is to cover the 1A, 1C, 1A, 2C, 3D, E, 4G, right? 5H. We cover the branches on the right. We cover all the branches on the right. Then we have another test case to cover all the branches on the left. 1A, 2B, E, 4F. So we cover all the branches on our left. So this is a branch coverage. We need two test cases to cover all the branches, right? The path coverage is more complicated. Basically, we need 4 test cases to cover all the paths because there are lots of paths, right? So first branch you go to left, then the second branch you go to left again, but you can do another combination. First branch you go to left, second branch you go to right, or like both branches go to right. Very different combinations. So many combinations. So path coverage, in theory, it's possible, but in fact, it's usually not possible. It's usually feasible for very small programs, but for large programs, it's impractical. Okay. So most cases we discuss about line coverage or statement coverage, right? Or branch coverage. So the two coverages we usually discuss. Okay. And for coverage tools, right? For example, for Java, we have many tools. Like one of them is Jacoco. So some of you may already use Jacoco in your TP1, right? So Jacoco is a way to measure the test coverage. Okay, and there are different other tools as well, but the most famous one, like an open source one, is Jacoco right now. Okay. And just we need to know a little bit about the Jacoco. It's a free code coverage tool for Java, right? It can do coverage analysis of branches, lines, methods. Also can calculate the cyclomatic complexity. It's a complexity measure, okay? And you can have a report in HTML, XML, CSV. So if you're reporting HTML, it's easier for you to to look at it, right? If you save your report in XML or CSV, it's easier for you to pass the result automatically. Okay, and Jacoco is integrated with many tools like Ant, Tasks, Maven plugin, and Gradle. Okay, so yes, it's usually used as Maven with Maven and Gradle in the continuous integration in your test environment. Okay, and so I want to show briefly how it works, how it's general like for it's not just for Jacoco, for many test coverage tools, how it works, right? How we can magically measure the coverage of the tests. So basically, so we write the Java file, right? Or like write the C file, right? So after it compile, for C, it compiles to the O file, right? And for Java, it's compiled to the class, okay? Then what Jacoco does, it will add some instrumentation, add some extra instructions in the compiled file, right? So this instrumentation is just to record what happens in the program. So which line is executed. That's simple. Just do this recording. So you can either instrument before the execution or do the instrumentation on the fly, which means do the instrumentation while it is running. Okay, and then it run a test, and generate the results, and then do the analysis. So it generates results. The results shows which line is executed by which test case. Do the analysis, do some calculation to measure the line coverage, branch coverage, etc. Okay. So this is basically how Jacoco and other test coverage tools works. Okay. Okay. So we talk about code coverage. We just briefly mentioned it because we already have simple and we already have some experience on it. All right. So there are some discussions about code coverage. The first one, is it always possible to have 100% statement coverage? Right. Think about it. Is it always possible to have 100% statement coverage? Is it possible to have 100 branch coverage? And is it possible to have 100%, sorry, not patch coverage, path coverage, okay? So anyone can tell me your answer. You can either raise your hand or put it in any chat channel, okay? The answer is, it is not possible. It is usually not possible because, for example, you have many parts of the code that are unreachable, right? And it is very difficult to design test cases that can cover all the parts of our program, okay? Next, does a 100% statement branch or path coverage guarantee a bug-free program? Answer yes or no. Think about it. Okay. I just click something wrong. So you can see the slide, right? Okay. The answer is no. 100% coverage cannot guarantee a bug-free program because you just cover this branch or this path or this statement. It doesn't mean you measure completely about the correctness of the program, right? For example, the program may have one variable a equals to 10, right? And you assign, for example, a variable a, you can input a value to a. The value can be from 1 to 10, right? use that any value, and this line will be covered, right? But the result may not be correct. It is good for one, but if you input 10, it may be incorrect. Okay, so 100% coverage doesn't guarantee bug-free program. Okay, there are also more complex coverage metrics proposed but not commonly used, usually statement or line coverage and branch coverage. Okay, so why do we measure coverage, right? So one way is we want to know how good the test cases are, how well they can cover our source code. Also, code coverage is very useful for other tasks. These other tasks include automated test generation, spectrum-based fault localization, test case prioritization, and test case selection. So we'll talk about each of them briefly. Okay. Um, First is automated test generation. So we normally we write our test case manually, right? Like we write JUnit test cases, but sometimes it might be extra work, or it's like too much work to write test cases and reach a high coverage. So there's one domain, it's called automated test generation. So we use tools to automatically generate test cases to test our program. Okay. How do we run automated test generation? So one way is called fast testing. What is fast testing? So fast testing generates lots of inputs automatically, and to exercise these inputs against the program. Okay, these inputs can be valid or invalid. Okay, so how it works? Basically, it's a generation based, right? So it can be generation based or mutation based. For generation based, it use some input models like grammars or file formats. It has some templates. You can say some templates to generate these test cases. For example, templates can be okay. This input can be this variable, and you can change it in this way. This is like a template based or generation based. Second way is a mutation based. Mutation based is basically you have your existing test code. A mutation based generation, mutation based generation of test case would just do changes on your existing test cases, do small changes. That's called a mutation, right? Each change is a mutation. So in this way, you can generate test cases. For example, if you in your test case there's a, a random bit, right? There one bit, and you can flip this bit from 0 to 1 to generate another test case. Okay. And what about the test oracles? How to get oracles? Test oracles are already the existing test cases. Right? We can use existing test case as an oracle to generate a new test cases. This is a fast testing. So here I don't go to the details. I just want you to know there's something called fast testing, how it can be applied, okay, how it can be used. And how can we use fast testing? So fast testing is usually used to find the vulnerabilities in the source code. Because if you have a vulnerability, right, and if you change something in your test case and you find a big problem in your source code, and if you don't fix it, other people, hackers, may take advantage of this problem, right? So fast testing is widely used to find vulnerabilities. For example, there's a famous bug called Heartbleeds. Actually, the Heartbleeds killed many people. This is a medical system, and a bug in this medical system actually killed many people. Okay, so Heartbleeds could have been found by a fuzzing tool. This bug, the name of the bug is Heartbleed. If we apply fast testing on it, bug could be detected, right? But actually, at that time, this is old bug. At that time, fast testing is not still it's not popular. Okay, and recently people use a fast testing to test a self-driving car. Right? So, for example, if you look at these two images, the one on the left, this is the original test case. Right? This is the original test input for self-driving cars. The figure on the right is we add some fuzzing. We actually do some mutation to change some part. You can see a ring added, right? So the ring is added to this figure. So it actually generates a virtual test case where there's a ring, but in the original case, there's no ring, right? This is a mutation. This mutation is adding a ring, okay? This is one example of fast testing. Right? So why we talk about fast testing and why coverage can help fast testing? Because how we generate fast testing, the criteria is to increase coverage, and the coverage can get fast testing, right? So the goal of fast testing is to find new path. You automatically generate your test cases to detect to cover more path, right? So you can use code coverage measure to measure whether you increase the coverage of a path, whether you find a new path, right? This is how code coverage is linked to fast testing, okay? So basically how it works. First, we instrument the program under test to record code coverage, and we apply fast testing, right? We apply fast strategy. When new path explored, we use a new path as a starting point to do more mutation to find more new paths. Okay. This is a general introduction about fast testing and how code coverage can help fast testing. Okay. The second application of code coverage is fault localization. What is fault localization? So when there's a bug in the software, right? Some customer or some users report a bug. And so one way is we look at the code and we take some clues from the report and we try to find the root cause of the bug manually, right? But manual effort, so we try to avoid manual effort if possible. So one way is to automatically locate the location of the bug. It might not be 100% sure, but at least we can provide some guidance, right? To giving a bug, giving some symptoms of the bug. So we want to automatically locate the bug in the source code. Okay, so formally, we can define this problem in this way. So giving a set of test cases, one or several test cases will fail. So each failed test case trigger a bug, right? One or several test cases will fail. So where are bug lines based on our failed test cases? So where are buggy lines? How to locate this bug? Okay, so here, there's a, look at this table, this figure. On the left, so these are statements in a program. This is a piece of source code, right? On the right, so we have test data. Each column is a test. And the gray area shows that these test cases cover these lines of this program, right? And the white area shows that this test case doesn't cover this line of this code. So you can see we have different test cases, different input combinations, and we have the test result. The first 5 test cases pass. The last test case fail. Okay, so how can we determine which line has a problem, right? So probably, so you can imagine that this buggy line is associated with the last test, right? So we can look at their lines covered by their last test. But there are 6 lines covered by their last test, right? So how can we determine which line it causes a problem, right? So actually what we can do is we can rely on a score or a metric here. So let's discuss about the metric, okay? Yeah, coverage-based fault localization. the intuition is statements that are primarily executed by failed test cases are more likely to be faulty than those are primarily executed by passed test cases. Here, look at primarily, right? Okay. So just take one second to think about this intuition, right? So this is a straightforward intuition. Okay, the solution is we rank the lines in the source code based on their suspiciousness. Okay, how to define the suspiciousness? Okay, so their suspiciousness is equal to is described in this equation and this formula, right? So basically it is um, how likely this line is associated with a few test cases, while it is not very associated with the past test cases. The formal definition is here. We use for this line, right? We use number of field test cases divided by the total number of field test cases, right? I mean, the number of field test cases that execute this line divided by the total number of field test cases, and this divided by the same thing, the number of field test cases executing this line divided by the total number of field test cases plus the number of test cases executing this line, not the past, divided by the total number of past test cases. Just look at this formula and check. So basically, this is a ranking of the suspiciousness. The intuition is that if this test case, if this line or this statement is primarily executed by few test cases, then it is more likely to be faulty than those are primarily executed by past test cases, right? Let's look at an example to see how it works. So here, if you look at the first line, right? The first line is associated with one field test case, right? And the total number of field test case is one, so it's one divided by one, right? Then the total number of past test case is five, and this line is also associated with all the five past test cases, right? So the score is 0.5. But if you look at their line, the seventh line, right? M equals to Y, right? Here I have a comment, it should be X. They're just bad. Look at this one. So we find that the total number of past test cases associated with this one is only one, right? Only one past test case is associated with this line. So this is only changed to this formula, right? Then we get a score or a suspicious score of 0.83. So we say that this line is the most suspicious line. This line is most likely to be associated with a bug, okay, or associated with the failures. So this is how we calculate the suspiciousness. Okay. So here I mentioned the tarantula, right? This is a tool to manage test cases and to measure test coverage. Okay. So any questions here? Okay, let's continue. Okay. The third application of test coverage is test case prioritization and test case selection. So why we want to do test case prioritization or test case selection is because sometimes we have so many test cases. For example, in our regression test, there are there might be a lot of them, right? So in our continuous integration uh, environment, we may not be able to run all of them. Can we just run part of them? If you just randomly run part of them, you may not be able, you may reduce the coverage significantly, right? So that's not what you want. That's not a reason why you want to uh, reduce test cases, right? So in fact, we need to prioritize these test cases in order to reduce the test cases that need to be run, and while at the same time we want to ensure that test coverage is high. Okay, the same thing for test case selection. Okay, which are called TCP and TCS. P for prioritization, S for selection. Okay, this is a problem we just mentioned. How can we do this, right? So one rationale is that the changed files are more likely to introduce defects. For example, um, I mean, in a continuous integration environment, like in a like a issue, version control environment, we just recently we changed these files. If we just recently change these files, we can just run the test or prioritize the tests that impact the recently changed files. In this way, we reduce test cases, but we increase the coverage of the recently changed files, right? Uh, the one type of solution is TCP. One type of solution is TCS, or TCP is test case prioritization. For example, we can reorder test cases and prioritize the test case that execute the change files. This is TCP, right? Another type, TCS, for example, we can select a subset of test cases and maximize the coverage of the change files and minimize the executing time. Okay. Similarly, these two approaches similar, TCP and TCS. Okay. Let's look at a concrete example application at Microsoft. Okay. Um, So how it works, basically, it uses approach to uh, to measure the coverage information from the old version, and then it uses the result to predict the coverage information of a new version, right? So when it runs the test case for a new version, you just use the predicted results, use the predicted coverage. This is how it works. And the result is see uh, there's two approaches, right? So in this approach, so here the vertical inner figure on the right, the vertical is axis shows the number of the percentage of defects detected. Okay, then um, axis shows the sequence of the versions. Okay, so this sequence are run in order. Okay, so we run these tests in order. If we can see that. Uh, so here, I just want to mention that for each sequence, there are multiple test cases, right? And we can look at here. The first sequence is able to detect 80% of the defects, right? So this is a prioritization, right? We run the first sequence first, then the second, then the third, then the fourth, right? If we just run the first sequence, we already detect 80% of the defects, right? If we don't run the rest of them, then we still have 80%. That shows the effect of using test case prioritization to reduce the test cases. Okay. So here it distinguishes the number of percentage of defects and the percentage of unique defects. Right? So you can see that running the low priority test cases doesn't significantly increase percentage of unique defects detected. Okay. So if you want to look at details, you can visit this paper. Okay. This is another approach. It's adopted by many Apache projects, and it use a test case selection. So in the previous video, they are using test case prioritization. In test case selection, so we see that there are, if you look at these figures, um, the pink line shows the runtime, that the runtime and the running, the number of tests that when you are running all the test cases, right? And the other two lines shows when you choose method or classes as a test case selection criteria. You can see that if we choose the method way, right? If we choose a method way and class way, we can significantly reduce the number of test cases and significantly reduce the testing time. Okay, right? But we still ensure a high coverage. This is you don't need to know the details of test case prioritization and test case selection. So we just want to highlight that using code coverage, we can do code test case prioritization and selection. We just want to ensure a high coverage, but reduce the number of test cases. Okay. So here I just want to, so any questions here?